你跟哪？是不好意思，我请问一下，在这边不知道有人讲到一个学生证吗？我这边
在这开始欢迎什么时候掉？我可以问一下。没有啊，他们我们才刚来要上课，所以他们应该不是第一次进这个教室的。你可以，哇，这个应该如果人家捡到会教。3楼有职工系，你是哪一系的？对啊，你可以3楼系办问看，因为这个是对全校开放的，所以你要查就查这个教室昨天下午是哪一节课，对，好不好？到学校看看，这个 sorry。 好。Hello。我开始录了，怎么把这个放上去？不是，我那个对啊，我没有看过韩进怎么弄。对，没有播放出去。
这个有插到？
有。好。在哪边播放？是投影片吗？这个吗？
他之前都没有插讯。
对啊，有啊，他已经插了。来，这我放上去了。没有你在我还不能上啊！
上去换一条。
没有你在我还没办法上课怎么办？原来线坏掉。
对。
那
有了？
哦，有了。Okay. Yeah. So let's continuing our frequency domain filter design. Okay. So you have last time we talked about a homomorphic. It's just kind of understand your image contains two parts of the component. One is the illumination. So illumination is from the source light. So it's the variation is slow. Okay, so it is located in the low frequency part, and the other part is the reflectance. So when the light source shooting on the object, they will have a reflecting, and depending on the your object, they have a lot of variation. So it's most of the reflection component contained in the high frequency part. So we usually design a filter like this one. Try to take away part of the low frequency part and maintain most of the reflectance. So it's a homomorphic filtering idea. Okay, so the equation you can look at this just like this one to design this kind of filter. Okay, so next one is try to combine the low pass filter and high pass filter, and we call it band selection filter. Okay, you are going to select part of your frequency band to pass through it or stop it. So we have two more different type of filter. We call it a band stop. Stop or band pass. Sometimes band stop we also call band reject. Okay, so you are going to define which part of the frequency band you are going to remain or going to remove it. Okay, so here is a very clear profile of your filter. Like the left one, this is the ideal band stop. Part of the band will be stopped. And this is the corresponding Gaussian design band stop filter. But we will see some details in this information. So you can see you design this ideal low-pass filter, ideal band stop filter. It should be very easy, right? You can design to combine this by low-pass filter and high-pass filter with two different frequency, or you can design two. So here is the field equation for the ideal low-pass filter. Try to use low pass through part of it and high pass part of it and summation it, so you can have a two part of the command result. So here you can design a low pass with this cutoff frequency, and the other one with the high pass filter, filter with this cutoff frequency, and combine the result together. Sum up together, you will get this band stop, band reject filter, right? Low cut point 1, C1, and the C2. So low pass filter for the C1, and the higher C2 for high filtering filter, and combine sum of the result, you can get this one. This is can be right on like this equation. So it's ideal band reject filter. How about design a Gaussian filter? Gaussian band reject filter. So here is the idea. So if you see the Gaussian is we always have the Gaussian in the center. Its center is a 0, right? Okay, it's a symmetric function. But now you are going to move a little bit of the Gaussian to the right part. So what do you get? So it have a Gaussian bell shape like this one. Center here is C0 here, right? It's symmetric. And you just use 1 minus this one, can easily get a band stop. So how you do this one? This is the Gaussian filter, and then 1 minus Gaussian filter. What's the result? So you can get this one, exactly this shape, the bell shape upside down, right? Very easy, intuitively, you can get this filter design. However, please look at this one. Also, you can have the two Gaussian to get this result as well. But if you look at this one, if you 1 minus this Gaussian filter, what's the result? We'll have some of the low zero frequency is not like our original expectation. It should be 1. So how can you do that one? Oh, this one is combined two Gaussian filter together. This one is a 1 minus Gaussian filter. You get this filter easily, but the result doesn't as ideal as your expectation. There should be 1 at the 0, at the 1 at the 0 frequency here. But unfortunately, if you 1 minus this Gaussian, the result will come up like this one. So how can you solve this one? It's easy to do this one. Is do some multiplication. Your Gaussian should be like this one, right? The original Gaussian filter, traditional one, should be d squared minus d u v 2 sigma. Okay, so it's a square here, and now we just change to this format. Change this one to C0 here. C0 here, which means you are going to shift the Gaussian bell shape to the right hand side. So the C0, the bell shape symmetric will become here, 0 here, and then but unfortunately you cannot get this result at the 0 frequency as the constant 1. So you can just add back. You can see if I put this 0 here, so here is some 0 minus something square. There's still some value here. It's not equal to 1. So 1 minus this value will become some little value remain. So that's the reason you didn't get a good one, good filter like this your expectation. So and also it's for this infinity, the W here, you are going to change this one should be a W square, original W square, but you are going to modify a little bit, like this one times D value here. So when your D go to infinity, also this will give you some good value there. So go to infinity, then go to 1, 0, right? Infinity, so it's an e to 0. So it's also, you can get a 1 minus 1 become 0 in the, it becomes 0 here. Infinity minus infinity becomes 0. So 1 minus 0 is go to a good design here. So it's a way to try to solve this problem. And you can do some multiplication to get this ideal band reject filter from the Gaussian function. Okay, so if you look at this one filter design, and they will get like this 3 profile perspective plot of the ideal and the modified Gaussian, and also Butterworth as well. This is from Butterworth. So it's some modification here. This should be D squared, but we times the width here. And this is some shifting there, shifting of the C0. So you can just apply DUV as 0, DUV go to infinity, and see this also the Butterworth Lopez filter change, and it become a very good band reject filter as well. So you have a Gaussian Butterworth, and it looks like this profile, 3D profile, and also look at it as an image, and it should be something like this ideal Butterworth and the Gaussian band reject filter. So when can we use filter on our image? What kind of condition you are going to band reject filter? Like this one, this image. So if you have some image like this, and you can immediately imagine it, there should be some noise signal located like a repeated pattern there, right? So you see some repeated pattern, and this kind of periodic pattern, their energy should be focused on some specific frequency component. So which means if you look at the Fourier transform of this image, should be like this one. And there are some points with some specific energy in the frequency spectrum. They should have some conjugate relationship. So they should be mapping each other. So it will not occur only one spot point. So this kind of energies come from where? Come from this kind of background noise. This kind of noise is periodically. So they have some regular pattern occur in your image background. So you can easily remove this one by band reject filter design. So you say, I'm going to remove this filter located at this one. So this called, also another name is called notch filter. Band reject filter, some article, they say it's a notch filter design. So you just try to locate a specific frequency location and then remove it. And then if there's not only one noise over there, they are blue. So how can you do? You just cascade. So maybe you have a H1 band reject filter, and then times second one. So you can do this one continually, okay, cascade. So I'm going to remove this point. I'm going to remove another point, but just be careful. They have some conjugate, so you have two notch location you have to remove. So once you know there's a band reject filter design, and you just multiply it together, and what the result should be, like this one. Okay, so you just remove, use band reject, Gaussian band reject, or Butterworth. Okay, so you've got this final result, and what's the corresponding image, just like this one. So you can see all the repetitive, periodically noise pattern will disappear, and most of the image will maintain well. So only the frequency component here, the spotlight, like the bright spots there, you just remove it. But just remind you, it's a conjugate, so you have to remove this one and remove this one as well. Okay, so your band reject filter just like apply to this kind of condition. And you will ask what's the band pass filter. So 1 minus band reject filter. You'll get band pass filter. Okay, easily 1 minus the other one. You'll get only specific point will pass through. Okay, there are some more example like this one. So when you get this image here. So what's the noise to you? So you look at this image pattern. What kind of image? This is Saturn ring. Okay, it's a star. 土星还是木星？土星。Okay, the ring of the star. And when you get it from remote sensing image as a sensor, and get this the image for the ring. So obviously there are some repetitive pattern noise image in this ring. Where's the noise? It's the horizontal edge. It's a noise of this image. So how can you do that? So remember, in space domain and free domain, they are exactly opposite. It's a horizontal line. Their energy will focus on vertical area. Okay, so if we look at this one, their corresponding spectrum of the Saturn ring image will look like this one. So we are not going to remove the original different original Saturn ring, but the noise is the horizontal line. So where is the horizontal line should be in the spectrum? Where should be the corresponding frequency spectrum of the horizontal line in a spatial domain? It should be located in here. The energy will locate in the vertical. And when you have a long line there, you have vertical energy distributed in your VU0 equal to 0 location. So if you want to remove all this horizontal line from your image, you are going to take away this energy band, the vertical energy band. So how can you design it? You design like this one. And why we have some space skip, some frequency jump over there, not exactly whole vertical band reject filter, because in the center here, the G00, what's that? The image after you transform in the frequency domain, in the center original spectrum image, it's a DC value. It's your original background, the DC value. Okay, so you are going to maintain that one. Otherwise, become all the DC value disappear. You will become a dark image. Okay, so we design a filter like this one. So it should be very easy. It's ideal band reject filter. Only remove the vertical strand from your spectrum, but remain the DC value layer. Don't remove it. So what the result will be? Just like this. So you just transform into your frequency domain. Look at the energy distribution. So now you know where is the line of here. It's corresponding to this slant edge of the Saturn ring. Okay, so but here we know the arrow is horizontal, so we can remove this vertical energy band here. So the result like this. So it's you can recover back the image without the periodic noise over there. Okay, here is another way to look at. We say it's a band reject. You remove all this horizontal line there. So if you want to look at what is the image located in this black energy band spectrum, so you can use this band pass filter. Okay, so only the vertical band of the energy spectrum will be saved, and then inverse Fourier transform back to original image. It looks like this. So this image is the vertical noise, horizontal line noise in this Saturn ring image. So you can see separately. Okay, so it just tell you you can do this band pass, band reject field design. All come from your Gaussian design there. Okay, so yeah, is there any question for this a frequency domain filter design. So as long as you know the low pass, high pass filter, I think it should be easy for you to design the band reject and band stop filter directly. Okay, so let's stop our chapter 4 here. So now we can change to the chapter 5. So, oh, thank you. Okay, so for the chapter 3, chapter 4, we have the image enhancement in spatial domain and fluid domain. However, now we are going to compare different terminology. We call it the image restoration. Okay, it's different from the enhancement, because enhancement is just based on your request, the user's request. Maybe sometimes you use low pass filter, make the image smoother and become look smoothly. But sometimes you are going to enhance it, try to for some pattern recognition. So you are going to use a high pass filter, but there's no standard criterion for the enhancement. It's depend on the viewer. So how you evaluate your filter good or bad is you have to collect a lot of viewer and then use some questionnaire and then answer the question and give the response from 100%, 100%, and then say this is very good, good, okay, and bad, very bad. So they have different evaluation from the enhancement result. But now we are going to use some different technique we call the image restoration, image reconstruction. So there are some standard criteria, and you can compare because we assume this is a very objective image processing technique. So you have to compare to its original image and see how you remove the additive noise, how you reconstruct your image from this degraded one. So most of the image restoration is happen when your image is degraded. So how you degrade your image? Maybe some distortion, maybe some additive noise. When you pass through your image from one node to the other node, you have some additive noise, and maybe you add some spike and salt and pepper noise. So how you remove this image back to its original one? We can evaluate objectively, very fair, and there are some like a SNR, signal noise ratio, how you improve it back to your original image, and you can compare how you remove how much noise from the degraded image. Okay, so this is the image restoration, and we are going to introduce a lot of linear degradation model and some noise model, different noise model, and then restoration in the presence of the only noise only. So we are going to separate because we are going to use a linear filter to restore your degraded image. And so we have a very specific pattern. So your image will be add some noise. Okay. So this is the unique image. They have some noise here. Only present only noise. Only noise here. So if this is very straightforward, you just look at the image model and noise model from the distribution. You will understand what kind of noise in your degraded image. But sometimes when you have some distortion, so your image may be like this, become F, have some filter layer and active noise. So we have two different degradation models. One is without the different noise degradation model. Sometimes it's including some additive noise. So it depends. And sometimes both of them occur together. So you're going to remove it and how you get it back and then become a new restored image. We call it the F hat. And then please compare F and F hat, how close they are. And we can say whose technique is better. Okay, so image restoration is just mentioned. Most image obtained by optical, electron optic means likely to be degraded. So it's an electronic device. We always have some process to transmit, to get it, to scan it. We have a lot of different degraded model there. So the degradation can be due to camera misfocus. So it's misfocus. So when you take the picture, you move it, you use the wrong focus to get the image. or some relative motion or motion blur and between the camera and object. So sometimes you are going to take a picture, you move your camera, your headphone, and you get the image smeared. So it's very easy. Even you cannot read the object clearly, you can restore it. Very good result. I don't know. In this slide we have the example. So you see nothing there, but you know the direction of the motion blur, and you can recover back into original one bit, and you can see the image content. So like the vehicle drive very high speed through the highway, and then your camera take it, maybe it's become smeared pixel. But how come? If we know the speed, we know the direction, we can try different recover, removing restoration filter, and we can get back the original image easily. Okay, so it's sometimes we also have additive noise in the electronic sensor, atmospheric turbulence. So some active noise, we are going to remove it as well. So the goal of the image restoration is relatively clean the image from the degraded image. So this is what we mentioned. Involve a technique like a filtering, noise reduction. So we are going to have go inverse filtering and some noise reduction techniques in this chapter. So restoration is a process of attempt to reconstruct or recover the image that has been degraded by, we just mentioned some different degradation phenomenon. Okay, like the environment, like your hand shaking, blah, blah, blah. We can also restore the image. Involve modeling of a degradation process and apply inverse process. Okay, so that's we are going to learn how to design your restoration filter, the inverse process to recover the original image. And the criterion of goodness is required that recover the image of an optimal fashion with respect to the criterion. So we say how good it is. There's some scientific way, some digital value you are going to calculate. So removal of the blur by applying the deblur function, blah, 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 you use different restore technique, and then recover back to the original one. So the enhancement we mentioned in the chapter 3 and 4. So it's a manipulating the image in order to take advantage of the psychophysics of the human visual system. So we just mentioned it's because of your psychological issue, your viewing depend on the subject, depend on the viewer. Okay, so these techniques are usually heuristic. So it's not a standard process. It's a heuristic. So you are going to look at your image and then consider what kind of image you prefer. So you are going to design low pass, high pass, or band reject. So it's usually a heuristic. There's no standard criteria. So like a contrastation, histogram evaluation, this all enhancement technique. Just try to enhance your image only. Okay, so this is very important model here. So it's a linear degradation model. We are not talking about non-linear. Otherwise, a lot of mathematical formula is not suitable for this condition. So what kind of linear degradation model? We just mentioned this FNN is your original non-degraded, no noise image. You always have this one. But unfortunately, when you pass through this one, you are going to have some degradation model. Like I just mentioned, you are taking the picture, your hand is shaking, or you misfocus. Always have different degradation model occurring here. So the image is become blurred, okay, misfocus. And then before you get this image, there are some another extra additive noise. So it's an important issue, additive noise. So maybe you have different type of additive noise there. We will see what kind of different environment have different additive noise model. Okay, and then finally, this is the only image at your hand. So you only have this one. You only have this one at your hand. So you don't know what's the original image. You don't know what's the additive noise model. So you only have this image at hand, GMN here. So how can you do? How can you do? So we'll try. So sometimes the image restoration is try and error. You are going to use different model based on your knowledge, and you use try to recover it to the best condition. So you use mathematically representation. You can see your original image combined with some degradation model convolution, okay, in spatial domains convolution, and then additive noise here. So in frequency model, you are going to transform because it's linear. So you can see some in frequency domain, and we have the degradation model, frequency filter, and frequency image. Add some the noise, active noise. So it's in spatial domain and the free domain, you have this two standard restoration model, image degraded model here. And we say this h of mn is a point spread function to blur the original image, okay, degradation image. So PSF is a point spread function. Okay, so at your hand, you have this observed image GN here. So how can you do? Okay, so the problem is given an observed image GMN, and you have to recover the original image back at FNN using your knowledge about the blur function. So you have to make a guess. Okay, based on your experience, you know what kind of blur function occurred in this image, and use some characteristics of the noise eta, and so you also have to find out what kind of noise model in this image. Okay, how can you do? Think about it. You have this image at your hand, like this one. Cameraman is blurred. It's not. It's very blurred image, and you are going to reconstruct. It's still blurred, but you can see the eye. Okay. So anyway, so if you have this image, very bad image, how can you do? We have a better example later. Yeah, how can you do? We just know this is a GMN, and it's degraded by some degraded filter, and some active noise. If you get this image, how can you do? So sometimes we have to think about the noise first. So if I give you this image, how can you see the noise? How can you estimate what kind of noise it is? How can you do? It's a very easy way to separate spike noise and non-spike noise. Okay, for this kind of image, this is non-spike noise. What is spike noise? Is like some salt and pepper noise, nonlinear noise there. So it's not spike noise. But how can you see? It's kind of is that Gaussian noise? Is that uniform noise? Is that Erlang? Is different type of noise model? What kind of noise? How can you see? So the trick is try to find a constant background. Constant background. Okay, in this image, maybe you can take a piece of this image, and then see the histogram of it. It's much more easier to let you make a good guess of the noise model. Okay, so you are not going to take a lot of variation background and to see the noise model. It doesn't help. You are going to take constant background noise. So is there any maybe you can take all this old break. So take this piece of sub image and then look at the histogram. It should be constant, right? Your expectation should be constant. However, it's not constant because there's some additive noise over there. So we will see later. So it's if you can do that. So if you know your image is composed by H combined F plus eta. So what can you do? How can you go back to F here? So the first approach, you should take away the noise and then inverse back. So if I were you, I will do this one, minus this one, and then inverse transform of the H filter. Okay, so it's become like this one, like this operation. So how can you do that one? So step by step, we are going to look at the noise model first. Okay, okay. So it's noise model. Okay. So first of all, we can see most of the general condition. Okay, with the expectation of the periodic interference. What's the periodic interference? We already saw that in chapter 4, the latest image, the Saturn image ring, right? If you see that image have some specific pattern continually, periodically. Okay, this is a keyword, periodic. 周期性 is a 周而复始. Periodic image is very clear. So like this kind of pattern, we also have the other one, the car in previous image, right? The car, you see a lot of repetitive pattern, periodic pattern in your background. You know there are some periodic noise, periodic interference. May I ask you what kind of the result in frequency domain, the periodic interference? What kind of it? So you have a sinusoid noise. So periodic is just like a sinusoid, right? So it's a sinusoid noise. Every periodic we mentioned in frequency Fourier series tell us if this is the periodic signal, it must be combined by different frequency of the cosine and sine of different harmonic frequency component, right? So they have a main frequency and the twice of the main frequency and the triple fourth. So it's always have some if you have a periodic pattern, so you can represent this noise by Fourier series, and it's combined by some sinusoid signal and their harmonic wave signal there. So this is a Fourier series, Fourier mathematics. The first idea is a periodic signal always combined by the different fundamental frequency component and their harmonic wave. Okay, omega 0, omega 2, omega 0, 3, omega 0. So like this repeated pattern, you see it should be combined by some sinusoid wave. What's the sinusoid transform, Fourier transform in frequency domain? What's this kind of wave? It's a spike, right? It's a spike. So always we say if you see some repeated pattern noise in your image, you will see some bright spot in your frequency spectrum. We just have this car image with a lot of repeat periodic interference, and they have some location of the bright spot. Okay, bright spot. Sorry, bright spot noise. You just remove that noise, you can get it back. So if we look at with exception of the periodic, if we don't look at the periodic one, so how can we see? Like this one, there's no periodic noise there. So we have to look at the background. We will assume the noise value are uncorrelated from the pixel to pixel with the uncorrupted image pixel value. So we are going to assume if there's no periodic signal, which means with the location there, they have no relationship, because your periodic signal, they will have some correlation with the location. But if it is not a periodic, so we assume it's uncorrelated from pixel to pixel. So which means there's the noise in different locations, they have no relationship, they are uncorrelated. Okay, that's first assumption. Usually made in practice and simply simplified analysis. This is a practice always like this one. Your noise is not periodic, so they are uncorrelated to your location, the pixel. So with the same assumption, they only describe the statistical property of the noise. So we are going to look at the statistical property of the noise. Okay, i.e. the probability density function. Okay, so how can you evaluate the statistics property of your noise, background noise? So we are going to look at the PDF, probability density function. Okay, so that's what I said. You just take a part of this constant, suppose constant background, and then put this one in the histogram distribution. You look at the histogram, you will see the function. Maybe immediately you will see it's like a Gaussian shape distribution. Okay, so it's not that so beautiful. Maybe it's like this one. So the noise, the histogram distribution like this one. So immediately you know it's symmetric distribution of the noise, and it's Gaussian. And if it is Gaussian, you have to find out what. There are two parameters for the Gaussian. Okay, the first is sigma. Sigma is the variation of the Gaussian function. The other one is the average value, eta, mu and the sigma. So mu is the Gaussian center value here, mu, and the sigma is variance of this Gaussian function. So you are going to evaluate the Gaussian function by these two parameters. Also, you are if you look at the noise model, it looks like a Gaussian, and the only thing you have to do is try to find the mean and the sigma of the noise model. Okay, so the square standard deviation we call the variance, right? So sigma is the standard deviation, so you can find for a Gaussian probability density function, approximately 68.3 of the value are within the one standard deviation. So which means in this center here, okay, so this about 68.3%, and for 2 sigma, and it's almost 95%. So it's around the mean value. Okay, so this is the Gaussian probability. So the second model is like this one. So if your noise model is not symmetric, it's a little bit biased, okay, and then like this shape, okay, your noise model is like this one. It's called Rayleigh noise. Okay, Rayleigh noise is use this equation to represent. So if you look at this one and look at their shape, the noise model shape, can you expect it's like this one? So put a z, the noise variant parameter is z. So put a z equal to a. When z equal to a is a 0 here. Okay, and z equal to a, and then increasing until this value a plus 2b divided by 2 and take a root, and then you can put there a plus b blah blah blah, and you will see the highest value will be this one. So it's this kind of model we call it the Rayleigh. It's like some imagine laser application have this kind of Rayleigh noise. So it's look at the different shape of the noise, you can estimate what kind of noise model. And also this one has some variance and mean value standards. So you are going to calculate by yourself. We are not going to go through this one. So when you want to calculate the mean value, I think you can do this one, try to find out. And you want to find out variance. This should be S squared, and then the PDF function, and try to evaluate the variance and the mean value of your noise model. So here we provide the result of this corresponding noise model for the Rayleigh noise. Okay. So this is the second type of the noise model. And the third type is the Erlen, okay, gamma noise. So gamma noise is like this one. The other one, this is one side noise. It's not like the Gaussian in two sides, positive, negative, positive. So your data will be add some noise and minus some noise value. But this one is positive, always in the positive one. And the next one is a gamma noise. So gamma noise, the formula PDF for the gamma noise is like this one. The factorial there. So what's the value? So you can see when it's equal to z equal to this value, and they have some noise like this one. Okay, early noise, and east also is in the right hand side of noise. So the factorial here is you know how to calculate b minus 1 factorial. It's if you have 5 factorial, it's 5 minus times 4 times 3 blah 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 times 2 to 1. Okay, so this is the gamma noise type. Okay, A always have to larger than 0, and B is an integer number. Okay, so this mean value of this one is B divided by A. So this noise type, the mean value is B divided by A, and the sigma is B divided by A squared. So it's all mathematics standard noise type. And you can see it's also one side. It's not like Gaussian in two sides, positive, negative, and it's all one side. But the density is skewed in the other direction. Okay, so it's not symmetric. So it's not symmetric as well. Okay, so it's always based on your noise model, and you know how to remove it. The next one is exponential noise. So if you look at your background noise like this one, active noise like this one is exponential. Sometimes longer. So this shape noise we can easily to see it's an exponential format, right? A times E minus AZ. Okay, for this one, A must be larger than 0, and we have this kind of shape. And the mu, mean value, and the sigma square, the variance, also can be calculated well. So this is exponential. So the next one is uniform noise. So if your noise look like this one, evenly distributed in certain range, and we say it's a normal uniform noise. Okay, normal is Gaussian. Okay, uniform noise. Uniform noise it can be described by this mathematical formula, and the mean value will be the center of this part. So it's a plus b divided by 2, and for the variance is b minus a squared divided by 12. So it depends on the noise distribution, and you can calculate. So if you can see the model like this distribution, you know it's a uniform degraded noise. The next one is impulse noise. So we have 5 different noise model. So impulse noise must be easy look at from the degraded image. You can see some light spotlight spot and some dark spots in your image. And for this noise model, we have to use probability to describe it. So the added probability is 1, right? So it depends on what's the distribution of your white spot, the salt noise, and the black spot, the paper noise. So we always say this is salt noise, this is paper, salt and paper noise. So it's located in different range in your image, and their probability should be added up like 1. So it's depend on your distribution of the salt and paper. So it's like this one. So how you do that one? So we say if we ignore the degradation first, the filter first, we only look at the noise, additive noise model here to your image result. So how can you see? So it's like this 6 different noise model, as you know. So we can compare. They are different. If you look at the shape of the noise, you can see, oh, this is different model noise, and we try to remove it. So here is the example. The test pattern used to illustrate the characteristics of the PDF, the probability density function of noise. So this one is this should be clear one. Okay, so if they put this one here, so we have 3 different gray label in this image, and add some different noise model there. So can you tell me what kind of the noise model it should be? So from this image, I bet you cannot distinguish what kind of noise model there, right? So how can you do? We just tell you. You just use some sub-image. Look at it. Sub-image. Okay. Here we use very simple, straightforward, constant background value. So you can see it's like this one. So if you can see from the constant background, and you will see the noise model. Hopefully, okay, if they are degraded constantly, so the model should be existed with this image. So you can see, if you have see, oh, in 3 different color background, they have this kind of very symmetric distribution noise there. We know it's a Gaussian. Okay, it's some bias, okay, skewed, and this is from a little bit different. Okay, but how can I tell? I don't know. It's just your intuitive. It's a more straight, more vertical, like it's more slightly skewed. So it's a gamma noise and the relay noise there. So it's just tell you some example here. So the easiest way to characterize is the spike noise, right? It's some spot, salt and paper noise there. So if you look at their PDF distribution, you can see, okay. And this one is this corresponding noise model is should be exponential, and this one the result should be uniform noise here, and this one is spike noise, and you can see the noise model there. So as long as you know the noise model, you know how to remove it. Use the right filter to reconstruct. For example, like the spike noise, you never try use the smoothing filter. Okay, it's nonlinear, so you are never try to use the linear filter to remove it. So maybe some medium filter is better than this one. We will give you some different way to solve this problem of different noise model degraded image. Okay, I think we will stop here, and next time we are going to give you some idea of how to solve this restoration problem. Okay, yeah, we'll stop here.
请问吴定贤在吗？礼拜一的时候有人拿他的考卷吗？
没有连的。好。
可以跟你聊一下那个开会的事情，就是
我们今天有吗？
没有明天。
明天对，然后呢？
立委就是因缘机会认识了另外一位细胞意见师。
哦，
因为身份特殊。
谁啊？谁？你说谁？
立委认识。
真的、啊？
对。
OK， 很好。
亲戚。
很好啊。
的关系。
然后呢？
然后我们有。
他可以帮忙吗？
问怎么？
对。但那他是台湾那300-400了。
对对对，他说那个他也认识，就是开会的时候，
因为人不多啊，对，300多的。哎，然后呢？
他说他觉得不应该叫我们标，因为他说
是啊，
标这个
我们没有要你标啦，但是然后呢？
但因为我们没有标记啊，就我最近这几天，因为我们有问一下标的那个 criteria 嘛，就是他有给我们一些 normal cell 的一些图片，让我们去辨识。
对。
然后我这几天就是我跟立文都在传标，可是标的
我觉得你们也很厉害。
我觉得没有意义。
对啊，那个错误的标示也没用啊。
对啊，所以我觉得这礼拜
可以讲啊，提出来啊。我也觉得你们标你们，因为我看实在是太像了，连他们标都可能被确认。我就跟你讲，有一次病理协会，那个日本教授就问说，来，你们都是病理师专家。post 出来，然后这个情况是什么？大家就算，然后投票。
虽然每个都不一样。
uniform， 你如果说高检，我觉得还有这个是 uniform， 我吓死了。所以那个意思就是说，没有 standard， 每个人看的都是不一样。然后所以我是说，觉得应该是给你几个干净的标好了，然后我们从那开始，然后去慢慢的让它纠正还是怎么样，应该是这样比较对。可是你现在连 normal 都没有，那是很好笑的事。
对啊。
那是很离谱的事情。
他还有拍他的教科书，然后上面有 normal 的 cell，
然后
让我们去看。然后我们现在重新做标记，确实有
比较清楚一点，
有比较清楚，但是
还是不准。
他给我们
发炎啊，我觉得发炎跟癌细胞很难
分。
哎，你那个线错，线来。没有吧？
然后就
对，课本字呢，我也分不出来谁是谁，我也分出来，我从来不会去看那个啊，所以是我贴错了是不是？来，
因为我看
他说跟弄错了是不是？有可能啊。哦，真的，好，没有，这个他就是会，还是我贴错了呢？这一边是直的啦，一边是还是有一间客人在哦。然后呢，这边直的啊，这边有 curve 啊，对，这边两个是一样，为什么看起来是一样？
所以是上面这里不一样。
对，这个不一样，我觉得这个可能接受，对，好，我再找。
然后我有个问题，所以这是 frequency domain 转出来的结果？
没有，这 spatial domain， 这完全是看 spatial domain 的统计，这边都是 spatial domain， 是拿这个影像去看 histogram， 这里拿这个背景去看 histogram， 所以这边就是直接去统计。你看这边直接统计，
对，
这边直接统计就会这个结果。你看这边还有它的，
这是0，然后这是25。
对，这也不是0啊，它的黑点白点也不是25，但是你有没有看到那影像在这两边都有？
对，它实际上是因为他们其实这些数值是跟上面差不多，只是因为这两个太多了。
对，相对， 啊，这个不用看就知道一定是 spike noise。我说这个跟这个很难分，但是这个其实 uniform 还容易啦，可是我觉得还是蛮难的，看不出来啦。你要看背景，看它分布啦。哦，那这个分布其实这个当然是外加的啊，外加很容易去呈现，好不好？哦，这是 spatial domain 哦，不要搞错了。哦，
它是 spatial domain， 然后
histogram，对，看 histogram 就好了。对，只要看背景的 histogram 就可以看出来。
因为我在录影，我让他暂停一下。好，
拜拜，老师，拜拜。
你明天提出来啊。
好，我觉得明天一定。